Hi everyone, welcome to our next topic in ChemE 122, which is now our discussion on refrigeration cycles. So again, recall your refrigeration cycles. These are devices, okay, which take heat from a colder reservoir, and by adding work to your cycle, you now reject this heat to a hotter reservoir. So they operate in the reverse way as to how our heat engine operates. Okay, so this is our uh, ideal model for a refrigeration cycle, which is based on the Carnot engine. Pero na-reverse na natin siya, so we now have our reverse Carnot cycle, which is our Carnot refrigerator or our Carnot heat pump. Okay. And our Carnot heat pump, okay, or refrigerator operates in this manner. So from state 1, meron tayong isentropic expansion to state 2. Okay. And then from state 2 to state 3, you have your isothermal heat addition. Okay. Nag-a-add tayo ng heat dito, QC or QL. Okay. And then we have our um, isentropic expansion. And finally, we have our isothermal heat rejection. Right. So again, the Carnot cycle or the reverse Carnot cycle is composed of two isentropic steps and two isothermal steps. And ang net effect niyan, okay, so mag-a-add tayo ng work, net, the positive. Okay, papasok yung net work. So the work of the compressor is much greater than the work of this particular turbine. Okay, then we take heat from a colder reservoir and then we reject this heat to a hotter reservoir. So now if you want to operate your ref in a particular using a particular substance, okay, it's easy to do state 3 to state 4, the change, 3 to 4, and 1 to 2, the changes, simply by fixing the pressure. So when you fix the pressure, and kung isothermal yan, purely magiging phase change lang. Okay? However, this is a Carnot cycle or the reverse Carnot ref, or the Carnot ref is quite impractical, okay, because of steps 4 to 1 and 2 to 3. Okay? Kasi for step 4 to 1, you have a saturated liquid here. And the saturated liquid, okay, pag in-expand mo yan, magkakaroon ka ngayon ng mixture of vapor and liquid of low quality. And pag nalagay mo to sa isang turbine, hindi siya magandang gawin. Similarly, for a compressor, okay, the compressor will take in quality of fluid of low quality, not necessarily steam pala, okay? And then i-compress siya to saturated vapor. So it's difficult to achieve this changes in state na meron tayong increased moisture content, okay, or decreased vapor quality in either a turbine or a compressor. So with turbines and compressors, hindi maganda magka two-phase mixture. Okay, if you recall our discussion on steam power cycles, in turbines natin hanggang 90% vapor lang. Eto, nagka-turbine operation tayo, ano yan, mga let's say 10% vapor quality, which is not ideal. Okay? Tapos naman, if you really, so ibig sabihin nun, to operate this realistically, siguro, you have to operate it outside the two-phase region. However, pag nalagay mo sa outside two-phase region, mahirap na gawin yung isothermal steps. Okay, so with this, your Carnot vapor refrigerator is not an actual realistic model for the operation of refrigerators, okay, or the operation of devices that take heat from a cold space and reject it to a warmer space. So your air conditioners, they don't operate in the Carnot cycle or the reverse Carnot cycle. Okay. However, we can use the concepts of the Carnot cycle, okay, as the standard for evaluation of our actual refrigeration cycles. Okay. So now, our simple model for your ideal refrigeration cycle is known as our ideal vapor compression cycle. Okay. So what will happen here is that, okay, we can still retain the evaporator and condenser, okay, similar to your boiler and to your condenser doon sa Rankine cycle natin. Okay, kasi madaling mag-operate ng constant pressure or mas maganda mag-approximate ng constant pressure for these heat exchanger equipment. And a compressor can still approach almost isentropic operation. Okay, basta dapat vapor lang yung pumapasok sa kanya, tapos lalabas sa kanya syempre superheated vapor. Okay? Pero Yung sa turbine natin, hindi practical na mag-operate na mag-take tayo ng liquid, tapos i-expand siya para maging vapor flow quality. So instead of having uh, a turbine, okay, we can just simply replace that by an expansion valve. So this expansion valve is also known as a throttling valve. Okay, so the throttling valve, so wala tayong work na nakuha dito, simple pressure drop lang. So from a saturated liquid, okay, lalabas dito sa condenser, lalabas siya at vapor of low quality. Okay, as magre-reduce na yung pressure to complete the cycle. So now our ideal vapor compression cycle, okay, ito yung typical states natin. So we have you from your evaporator. Okay, the outlet of your evaporator, unless otherwise stated, is always a saturated vapor. Okay, saturated vapor lagi sa state 1. Okay, it can be slightly superheated, pero lagi minimum saturated vapor before siya pumasok sa compressor natin. Okay, and syempre, state 2 is always a superheated vapor, and unless otherwise stated, we assume an isentropic compression in our compressor. Okay. And then our condenser now, ito yung heat rejection equipment natin, nagre-reject tayo ng heat. Okay, so yung vapor na papasok dito, at this pressure, lalabas siya at the same pressure with at stream 3. Okay, but now stream 3 is a saturated liquid. Okay, and then saturated liquid expands, so meron tayong ditong low quality vapor. Okay, so unless otherwise stated again, i-assume natin is S1 is equal to S2 prime kasi meron tayong isentropic expansion in a compressor. Constant pressure heat rejection, so P2 is equal to P3. You have a throttling process. Okay, so lagi i-assume na H3 is equal to H4. Alright, and syempre for 4 to 1, okay, P1 is equal to P4. You have a constant pressure heat rejection or heat absorption rather in your evaporator. So sa evaporator, dito niya kinukuha yung heat from your cold space. Okay. So if you trace this now in a TS diagram, it should look something like this. Okay, nandito. So instead of having an isentropic expansion, isenthalpic expansion na lang tayo. So meron tayo laging increase in entropy. Okay, with this cycle. Okay, we really cannot approach system na walang si 3 to 4 prime ay isentropic kasi hindi siya practical gawin. So ito yung one of the limitations of the cycle. So talagang 3 to 4 meron tayong entropy generation. So you can now trace your simple ideal vapor compression cycle on a pH diagram. So imbis sa TS, pH to. So pressure versus enthalpy. Okay. So for example, mag-operate tayo at this particular pressure at state 1 at 0.02 megapascals. Okay? So at state 1, lagi siya saturated vapor, and then isentropic expansion. So you will follow the isentrope. So yung isentropes natin, ito yan, yung mga constant entropy lines. Okay? So these are the lines of constant entropy. And then, you now reach state 2, so working pressure ng ating condenser. Okay? So with the working pressure of our condenser, okay, we now have an isobaric cooling, okay, or isobaric heat rejection to your hot reservoir, okay, to state 3. Ayan. And then state 3, saturated liquid. Okay, tapos meron tayong throttling process, and the throttling process should occur vertical line lang na pababa. Okay, kasi constant enthalpy line natin is a vertical line. And then finally, to complete the step, so isobaric heating or isobaric vaporization of your state 4 to state 1. Okay, so this is what the pH diagram would look like for our vapor compression cycle. So again, ito yung itsura niya kapag pH diagram. So mas madaling tignan kasi meron tayong tatlong straight lines and then one isentropic line from 1 to 2. Okay, so with this, pansin natin, si 3 to 4, wala tayong work dito. Okay, wala tayong work producing step or wala tayong work requiring. Wala tayong work producing step rather for your ideal vapor compression cycle. So you only have one heat absorption step, QC, one work input step 1 to 2, which is your isentropic compressor, and then your heat rejection step, QH, to your hot reservoir. Okay, so now how do you actually operate your refrigerators or your refrigeration cycle? Okay, so let's consider now your refrigeration cycle. So meron tayong evaporator, meron tayong compressor, then we have our condenser, then we have our throttling valve. Okay, so ganito yung typical dock flow diagram. Ayan. So this is state 1, this is state 2, this is state 3, and this is state 4. However, okay, sa evaporator, kukuha siya ng, ito yung cold space natin. Okay, tapos ito yung ating hot space or hot reservoir or heat sink. Okay, so imagine nyo, meron kayong ref. Okay, so let's say yung ref nyo, gusto nyo siyang i-maintain at sabihin natin 2 degrees Celsius. Okay? Tapos ang hot space natin, let's say yung nasa likod ng ref, okay, this is now at let's say 30 degrees Celsius. Okay, so our TH is 30 degrees Celsius and our TC is equal to 2 degrees Celsius. Okay, kung Carnot cycle ito, 'di ba? The working temperatures of our cycle should be same with the working temperatures of our hot and cold space. So kung Carnot cycle 'yan, okay, sa evaporator, dapat yung temperature ng evaporator na to should be 2 degrees Celsius and the temperature of our condenser should also be 30 degrees Celsius, similar with our hot space. Okay. However, we don't have a purely reversible cycle. Okay. So now heat transfer should occur naturally from your cold space to your evaporator and from your condenser to your hot space. And for heat to flow naturally, dapat meron tayong temperature gradient. Okay? And we know this from our second law of thermodynamics, para maging feasible yung process, dapat heat should flow from hot to cold reservoir, from hot temperature to a region of colder temperature. So kung gusto natin mag-flow yung heat from 2 degrees Celsius na space to the evaporator, okay, dapat yung evaporator natin, the evaporator temperature should be colder than the cold space temperature. Okay? So with this, dapat yung evaporator temperature natin, okay, should at least be 5 degrees Celsius lower than the temperature of your cold reservoir. So yung temperature dito, okay, should at least be 2 degrees Celsius tapos 5 degrees Celsius less. So dapat at least negative 3 degrees Celsius yung temperature natin sa evaporator. And similarly, for your condenser, dapat yung temperature natin dito should at least be 35 degrees Celsius para yung heat transfer is from the condenser to your hot space and para yung heat transfer natin is from the cold space to your evaporator. So with this, we can ensure a natural heat transfer progression. Okay. So now, that requirement of the 5 degrees Celsius na temperature difference will now present a certain challenge in selecting the working fluid or our refrigerant. Okay? Kasi dito, hindi na pwedeng steam ang gamitin natin. So, bakit hindi pwede gamitin steam? So, for example, di ba, kailangan, let's say, 2 degrees Celsius to, tapos dapat negative 3 degrees Celsius rather, yung temperature ng evaporator natin. However, one condition that you have to meet is that the vapor pressure of your refrigerant at the evaporator temperature at negative 3 degrees Celsius should be greater than atmospheric pressure. So dapat, okay, kung ito ay vapor at negative 3 degrees Celsius, kung vapor siya, dapat at negative 3 degrees Celsius, ang vapor pressure niya is greater than 1 atm. Okay? Kasi if nag-ooperate ka ng ref in vacuum, it's possible na magkaroon ka ng air leakage into your refrigerator, into your actual refrigeration lines. And ayaw mag-introduce ng air sa yung refrigeration line kasi mag-decrease yung heat transfer properties ng ating system and mag-leak. Possible yung ano natin, refrigerant, which we do not want. Okay? So with this, you now have to select a fluid na at negative 3 degrees Celsius, okay, ang vapor pressure niya is greater than 1 atm or close to 1 atm or something like that. Or at 1 atm, okay, ang boiling point, okay, should be negative 3 degrees Celsius or less than this particular value. Okay? So this is one important factor that you have to consider when you're selecting the appropriate refrigerant for whatever cold space that you want. So kunwari, meron tayong cold space at 2 degrees Celsius, possible na iba yung refrigerant na kailangan mo if you want to maintain a cold space at negative 20 degrees Celsius. Kasi different organic fluids or different fluids will have different properties, okay, which should meet this particular condition. Na vapor pressure at the evaporator temperature should at least be equal to 1 atm. Okay? And another thing, okay, di ba, ko-compress natin siya dito sa condenser. Tapos dapat, at this point, di ba, saturated liquid, dapat hindi sobrang taas ng vapor pressure. Kasi pag sobrang taas ng vapor pressure na yan, okay, malaki yung kailangan mong work na input sa compressor. So, yun din. Okay? Pero mas importante actually is this selecting the correct evaporator condition. Kasi kailangan sumakto na at least 1 atm yung vapor pressure at the temperature sa evaporator outlet. Okay? So with this, the most common working refrigerants now are your CFC refrigerant family, okay, collectively known as Freons. Okay, so back then, meron tayo mga, these were ozone depletion kasi they have these are halogenated hydrocarbons. Okay, so we replace the fully halogenated carbons with now non-fully halogenated hydrocarbons. Ayan. So most common now that are used are R22 and R-134A. Ito yung most common freons used in the most chemical process industries or even their actual refrigerants or in your air conditioners even. Okay? So in some other cases, you can also select ammonia. Kasi pag maganda sa ammonia, it's quite cheap, okay? Maganda transfer properties niya, and madali ma-detect kung meron tayong leakage. Pero, yun nga lang, you have to be careful with ammonia kasi inherently toxic siya. Okay, so with this, we're not gonna be using steam as a working fluid kasi diba, at negative 3 degrees Celsius and 1 atm, that's a solid water. So hindi talaga pwede ang steam. So we will now use your refrigerants. So we have a refrigerant table, and for this course, we'll use R-134A as our main refrigerant kasi ito yung madami tayong tabulated values for its thermodynamic properties. Similar to your steam table, meron tayong R-134 table that you can find in our course pack. So with that, you have, when you watch the rest of these videos, please take those tables out, okay, so that you can answer the videos along. Okay, so now, how do you name refrigerants? Okay, so ano nga ba ibig sabihin ni R-134A? Are they just some randomly assigned numbers? So R-134A actually stands for tetrafluoroethane. Yan yung actual organic compound name. Okay, so you have a non-fully halogenated ethane. So how do you name refrigerant? So the first number, okay, stands for, it's the number of the carbon atoms minus 1. So ethane, di ba? So dalawang carbon yan. It's the number of carbon atoms minus 1. That is the first number. So 2 minus 1, 1. Okay, and then number 2, the second number represents the number of hydrogen atoms plus 1. Okay, so H atoms plus 1. So we have 3 minus 3 is equal to H, number of H plus 1. So you have 2 H atoms. Okay, something like this. And then number of fluorine atoms is yung last part. Okay, yung third number. Tapos A represents just an isomer. So meron tayong R-134A, meron tayong R-134 lang. Pero mas common na ginagamit si R-134A. Not sure kung ito yung exact na chemical formula. You can just double check online. Okay, pero not sure kung the exact isomer. Pero for the actual name itself, you can take this as it is. So R-134A again represents tetrafluoroethane. Okay, so for R-22 naman, since wala yung first digit natin, so pag 3 digits, yung first digit lagi ay number of carbon atoms. Pero pag 2 digits lang, ibig sabihin nun, meron lang tayo halogenated methane. Okay? Kasi diba, C atoms minus 1, 0. So number of C is 1. So methane. Tapos number of hydrogen atoms, okay, 2 minus 1 is equal to 1. So 1 hydrogen lang. Number of fluorine atoms is 2. Pero kulang pa tayo ng isa. Okay, na unaccounted atom to complete the valence of carbon. So kailangan pa natin ng isa. And the unaccounted atom is always chlorine. Okay, so with this, our refrigerant R-92 is chlorodifluoromethane. Okay, so let's now proceed to an example. Okay, so we have our ideal vapor compression cycle, which operates using refrigerant R134A as the working fluid. Okay, and operates within the cycle of refrigerant cycle between pressures of 0.14 MPa and 0.8 MPa. If the mass flow of the refrigerant is 0.05 kilograms per second, determine the COP of the refrigerator and the cooling load in kilowatts. Okay, so with this, similar to your steam table or your steam power plant calculations, okay, again, draw this table lagi of stream number, temperature, pressure, state, specific enthalpy, and specific entropy. Okay, so from this, that's now labeled kung ano yung mga pwede natin makuha from the given itself. Okay, so you're now operating between two pressures. Okay, and the ideal vapor compression cycle always operates between the lower cycle pressure and the upper cycle pressure. And the lower cycle pressure is always the pressure of your evaporator. And your evaporator is located, okay, or the process from 4 to 1. So therefore, P4 and P1, the isobaric yan, is equal to the lower cycle pressure, which is 0.14 MPa. Okay, so automatic na 0.14 MPa, C1 and C4. And similarly, yung ating higher cycle pressure is always the condenser pressure. So state 2 and state 3, yun yung 0.8 MPa. Okay. Next up, we always, unless otherwise stated, okay, kung ideal vapor compression cycle tayo, state 3 and state 1 should always be known. Okay, and state 3 is always a saturated liquid. And state 1 is always a saturated vapor kung ideal vapor compression cycle. Okay, keyword dyan kung ideal. Alright, so with that, you can now complete the states, okay, of streams 1 and stream 4. You can now read that from your refrigerant table, okay, from your saturated refrigerant table. Okay, and now, kung ideal to, so isentropic naman, C, 1 to 2. So S1 is equal to S2 prime. And so from here, we can now proceed with our evaluation of the other properties of our streams, which is now stream 2 and stream 4, before we proceed to our actual calculations. Okay, so unahin natin si state 2. So state 2 is an isentropic compression from state 1 to state 2. So S1 is equal to S2 prime. Okay, and you can now hanapin mo ngayon 0.8 MPa kung ano yung temperature and enthalpy magko-correspond with this particular specific entropy. Okay, so the specific entropy at 0.8 MPa, if you take a look at the R-134A table, okay, should lie between the specific entropy at the saturation temperature and at 40 degrees Celsius. Okay, so between Tsat is 31.31 degrees Celsius and T is 40 degrees Celsius, dito mag-lie si specific entropy na isentropic state. Okay, so from here, we can now interpolate to get the temperature and the specific enthalpy at state 2. Okay, so calculations again, similar lang din doon sa calculations natin for your steam cycles. Okay, pero iba lang yung working fluid natin ngayon. Okay, so next up, si state 4 naman. And for state 4, we have from state 3 to state 4, this is a throttling process. And for a throttling process, we have an isenthalpic process. So H4 is equal to H3. Okay, so yan, H4 is equal to H3. And then you can take a look at the saturated vapor table, saturated refrigerant table rather. And at 0.14 MPa, your specific enthalpy na 95.48 falls between the specific enthalpy of saturated liquid and vapor refrigerant. So from this, you can now obtain, okay, the quality of the vapor, which is 32.25%, and the specific enthalpy, which is 0.37972 kilojoules per kilogram Kelvin. So as you can see, meron tayong slight increase in entropy lagi with the throttling process. Okay, so from this, we can now actually obtain the COP, So the coefficient of performance, again, this is equal to, okay, QC over W. Okay, so pwede mo itong kunin in terms of the specific properties only, or pwede mo siyang kunin in terms of the actual flow rate or energy flow rates. Okay? Pero pag-isahin lang natin, okay? So to determine the cooling load, so the cooling load is based on QC. Okay? So with this is equal to the mass flow rate of the refrigerant times H1 minus H4. So QC is always H1 minus H4, specific QC, times M dot. Tapos the work, syempre sa compressor lang siya. So mass flow rate times H2 minus H1. And last, the heat rejection, QH, is equal to H3 minus H2 times the mass flow rate again. So from this, you can now calculate QC, W, and QH. Okay. So again, QCW are positive, QH is negative, and you can now calculate the COP, which is 3.9688. So now a possible variation of this cycle, okay, is what if, again, meron tayong isentropic efficiency na i-consider. So what if the compressor efficiency is only 75%? So how would this change our cycle? Okay, so when we now consider the isentropic efficiency of your compressor, okay, only state 2 will change. Okay, kasi the pressure at 2 and 3 should still be the same at 0.8 MPa. Okay, so the compressor will still achieve the same change in pressure, pero mag-iiba lang yung temperature natin. Okay, the state, possibly superheated vapor pa rin. Okay, and mag-iiba syempre specific enthalpy and specific entropy. Okay, so if the compressor efficiency is 75%, only state 2 will change. Okay, but we can still use the values that we calculated earlier for the isentropic compression state. And the isentropic state again will lead us to the actual values of our specific enthalpy and entropy of the actual state. Okay, so T2 prime is 38.99 and H2 prime is 275.40 kilojoules per kilogram. Okay. And from here, we can calculate the actual enthalpy using the definition of your isentropic efficiency. So 0.75 is equal to your ideal work divided by your actual work. Okay. And from here, you can now obtain the value of H2. And H2 is now 287.47 kilojoules per kilogram. And using this value of the specific enthalpy, okay, tignan mo ulit ngayon yung table mo at 0.8 MPa para hanapin kung saan nag-match si H2 na at 0.8 MPa and 287.47 kilojoules per kilogram. And if you take a look at your table, okay, this should fall between 50 and 60 degrees Celsius. So medyo malapit sa 50 degrees Celsius. Okay, but to get the actual value, let's interpolate. Yan, so interpolating. So T2 is 50.75 degrees Celsius. So meron tayong increase in the temperature lagi, which is always what happens in compressors. Okay, as you decrease the isentropic efficiency, dapat tumataas yung outlet temperature. Okay, and the specific entropy is 0.98262 kilojoules per kilogram Kelvin. Okay, so from here, makita natin na kung ito yung isentropic state na 2, your actual state is now from 1 to 2 prime. So mas nag-adjust siya to the right. So ito, kunwari si H2 prime, ito ngayon si H2 actual. Okay, so with this, pansin natin, tataas si work required and tataas din yung heat rejected. And based on this, we should expect that the COP of our ref should now decrease kasi for the same cooling load na na-achieve natin from 4 to 1, lumaki yung kailangan natin na i-add na work. Okay, so we're now getting less cooling than what we are inputting, or for the same amount of cooling load that you need or you require, you have to add more work since non-isentropic na yung operation ng ating compressor. Okay, so again, to determine the cooling load and COP, the same formulas earlier should hold true, except mag-iiba na yung value ni H2. Okay, so mag-i-increase si W, okay, and mag-i-increase yung QH natin. Ayan. So, the following values to. So COP is now 2.9766. So ang laki na din-increase in the coefficient of performance ng ating refrigerator. Okay? So with this, ang goal natin for most refrigeration cycles is for us to maximize the COP. Okay? So for the same cooling load, we want to sufficiently reduce the work input. Okay? And to reduce the work input, we have to change or manipulate our refrigeration cycle further, okay, which will be our topic for the next video. Okay? So with the next video, gagawin naman natin ngayon is for the same cooling load, how can we minimize the work input? Kasi the work input of the compressor, it will determine kung gaano yung kalaki or kaliit yung magiging value ng COP natin. So how do we save on the compressor energy? Okay, so that's it, and thank you for listening to this lecture.